The sound is Ramani. For you, how the sound is here. Right now, can you clearly hear? Can you clearly hear? You can put in the chat. Check one. Check one.
Yeah. Yeah, I can hear you, but whatever you are talking, it's coming in the YouTube.
Check. Right, right. No, no. That's okay. Check. Check one. Check 1, 2, 3. Is it loud and clear? Check 1, 2, 3. Check 1, 2, 3. Check one. Check one. The Zoom chat, put it to. Is it clear? 1, 2, 3, 4. Check 1, 2, 3, 4. Right. Okay. Test one. Test one. Good evening, everybody who is online. We will start in another 5 minutes. We'll start in another 5 minutes. Right. Good evening, everybody. Well, today we'll be doing the final optics practical, which is practical number 21. Now, practical number 21 is two parts. You have practical 21.1, which we will start with. Practical 21.1, which we will start with. This is finding the focal length of a convex lens using no parallax method. Generally, in the exam, guaranteed they can ask this. It is a very simple practical for you to understand, but also important. Okay, also important. Right. Right. Practical number 21.1. Practical number 21.1. Practical number 21.1. Finding the focal length. Finding the focal length of a convex lens. Finding the focal length of a convex lens. Finding the focal length of a convex lens using no parallax method. Using no parallax method. Using no parallax method. Using no parallax method. Right. Now drop your pens. Carefully observe. Now, before you do this experiment, guaranteed you must find the approximate focal length. Guaranteed you must find the approximate focal length. What do you mean by finding the approximate focal length? Listen carefully. We have a white screen here. There is a white screen here. There you go. White screen there. Normally in advanced schools, there is something called an optical bench. Strict schools, you have something called an optical bench. Now, majority of the schools don't have optical bench. No? Now, if you don't have optical bench, this can be your lab table. This can be your lab table. So you have a white screen. What we do is, we mark a straight chalk line. We mark a straight chalk line. And from this straight chalk line, what we do is, somewhere around the midpoint, we mark a chalk mark. We make a chalk mark. Okay, no? So here you go, chalk line. Somewhere along the midpoint, we put a chalk mark. After we put the chalk mark, what we do is, we place the support, or you place the wooden support where the convex lens is going to be. We're going to place the wooden support where the convex lens is going to be. So what we do is, here you go, convex lens is kept. So remember, these are thin convex lenses. These are very thin convex lenses. Thin convex lens. So we move this wooden support. And we focus it on a distant object. So what do you mean by distant object? Sometimes there might be a light source very far away. Now I remember when we were doing this experiment, we focused it on the cathedral dome on top. Because our school physics lab was facing St. Lucia's Cathedral Dome. We focused it there. So light rays coming from far, if I draw the light rays coming from far, there you go. Light rays coming from far, you adjust the position such that the rays will converge to a single point. So what will happen here is we get a clear intense image. We get a clear intense image on the white screen. So here you get a clear intense image on the white screen. Clear intense image on the white screen. Clear intense image on the white screen. Now what does that mean? If you get a clear intense image on the white screen, it means that from the midpoint, normally we take the midpoint here, from the midpoint to the screen, we measure the length, that is your approximate focal length. So this F here, the distance from here to here, midpoint of the wooden support, this is your wooden support. Wooden support. Midpoint of the wooden support to this particular point, this distance is your approximate focal length. Approximate focal length. Right. So now you know the approximate focal length. Now, if you know the approximate focal length, then what should you do? Right. What you should do next is, look at this carefully. Now you have the white screen. So what you do is, you now adjust the location of the wooden support. Adjust the location of the wooden support. Adjust the location of the wooden support. Now you have marked the approximate focal length, so you measure the approximate focal length. Make another chalk mark there. And here you have the length. Here you have the convex length. Here you have the convex length. Right. So white screen is there. White screen is there. Focal length is here. That is your approximate focal length. This is your wooden support. This is your wooden support. Right. Now look at the board. Now you place the optical pin. Now they give you optical pin. Now you place the optical pin. Now the midpoint or the midline is like this. This is the midline. You place the optical pin such that the tip of the optical pin, I'll name this optical pin P1. The tip of the optical pin touches this axis or your principal axis. Once it touches the principal axis, I start to look at the image from this side. I start to look at the image from this side. Start to look at the image from this side. So now I'm looking at this image from this side, like this I'm looking. What will you see? Now be careful. You're looking through the lens. What are you supposed to see? If I draw it here, that's your lens. That's the center line. You will see an inverted magnified image of the pin, because you can see this part now. This part is going through the lens. You will see an inverted magnified image of the pin. If I draw it here, you will see an inverted magnified image of the pin. There you go. Inverted magnified image of the pin. This is the image of the pin. Now we know the object distance. We have kept it here. This is the object distance. There you go, object distance. Now we need to find the image distance. Now you will say, sir, we can see the image. Yes, we can see the image. But where is the image? Right. You say image is somewhere here, sir. Here means where? You are looking through the lens. You can see the image here. To identify this image, we use this method called no parallax method. We use this method called what? No parallax method. Now, what is this method? Look at the word carefully. We use another pin. We use another pin. And we keep that pin like this in front. I'll name that pin P2. Huh? We keep that pin in front. Now somebody looking from this side can see this pin P2. We can see the pin P2. Also we can see the image. Also we can see the image. Huh? We can see the pin P2 and we can see the image. Okay. Look carefully. Image can be seen and pin P2 can also be seen. Pin P2 can also be seen. Right. So white screen is there. Image is there. Check one. Check one. Right, is it clear now? Can you hear? Is it clear? Ah. Clear? Clear? Okay. From which point you could not hear? From the beginning or somewhere here? From which point? Power line. From which point? All right. Okay, look. Right. Okay, no? Right. Okay, look. I'll explain again from the beginning. So this is what we do. We keep a white screen and we focus on a distant object. We focus on a distant object. Light rays coming from infinity will go through this lens and converge onto the screen. When it converges onto a screen, clear intense image is formed. Now, when a clear intense image is formed, that means all of you know, no? Parallel light rays will converge to a particular point. Parallel light rays converging to a particular point means it's converging towards the focal. Converging towards the focal means this here is your approximate focal length. That is your approximate focal length. So what we do is we measure the approximate focal length. Right? After we measure the approximate focal length, we move the wooden support to a new location. We make a mark there. Measure the approximate focal length. Measure the approximate focal length. And keep the pin slightly beyond the focal. Now, when you keep the pin slightly beyond the focal, what will you get? Inverted magnified image. Real inverted magnified image. So this image is formed here. Now I'm looking from this side. From the top part of the lens, I can see the image. Top part of the lens, I can see the image. Okay? Now, how do I know where the image is? To know where the image is, I use another optical pin P2. I keep the pin in front like this, and I move the eye in the lateral direction. What do you mean by lateral direction? Like this. Side to side. Move the eye in the lateral direction. Don't keep your head down, just move your head only. Yeah? With the body, you move side to side. Okay, no? Once you move the lateral direction, now here the image and the pin are not coinciding with each other. Since they are not coinciding with each other, there will be a relative motion. So when the eye is moved in the lateral direction, there will be a relative motion. There will be a relative motion. There will be a relative motion. What do you mean by relative motion? The image and the pin. Let's say this is the pin. This is the image. There will be a relative motion like this. Huh? There will be a relative motion like that. Right. Now what? Now we want to make this coincide. If you coincide it, that means that we can find the location of the image. So what we do is, we move the position of the pin. Because it's a new thing, I'll draw that as well. So here you have the screen. This is your lab table. Here you have the wooden support. Here you have the lens. Here you have the lens. Here you have the approximate focal length. Approximate focal length. Somewhere around the center here. This is the pin that you keep. That's pin P1. Object distance U. Image is formed somewhere here. Now I move the pin to this position. Now all this time my eye is close by, yeah? Now what? Now the image and the pin are coinciding. If the image and the pin are coinciding, this is what you will get. Image is a magnified image. Image is a magnified image. Pin P2 is here. Now I move side to side. Move the eye in the lateral direction. What happens? Because they are coinciding, when the eye is moved in the lateral direction, I and P2 coincide. Therefore, no relative motion. Now what? The image and the pin, P2, when I move my eye lateral, they move together. The moment they move together, we say what? They are coinciding with each other. Now what can you do? Now you can find the image distance. Now you can find the image distance. Now you can see, no? Object distance, image distance. Now what can you do? You can change the pin new object distance. Same way you can find new image distance. Like this, you change the object distance and you find the image distance. So you keep changing the object distance and you find the image distance. Once you change the object distance and find the image distance, now you have a small table. Now you have a small table. So here we go. Object distance, image distance. The higher the values, the better, but generally more than 6 values. And what you do is you measure 1 over U and you measure 1 over V. These two are calculated. Let's apply lens equation. 1 over V minus 1 over U equal 1 over F. Object distance positive, image distance negative, focal length also negative. Simplify this. 1 over V plus 1 over U equals 1 over F. What is your independent variable? You are changing the object distance. What is your dependent variable? Image distance. So rearrange this. 1 over V minus 1 over U plus 1 over F. This is your X. This is your Y. y equal minus mx plus c. Y equal minus mx plus c. Now you plot the graph. Plot the graph between 1 over u. Plot the graph between 1 over v. What kind of graph will you get? You are supposed to get y equal minus mx plus c graph. A graph like this. What are we trying to find? We are trying to find the focal. Easy. Y-intercept, write in black a bit, y-intercept, that is equal to 1 over f. Okay? So f is equal to 1 over y-intercept. Finished. Practical done. So in this practical, what are you doing? You are trying to find the focal length of a convex lens using real images. Okay? Using real images. Right now? So quickly I tell you before we start writing it. First what we do is, there is a white screen here. In support, you can put the convex lens. Draw a straight line using a piece of chalk. Somewhere around the center, you mark, place the wooden support. Focus on a distant object so that a clear, intense image is formed on the screen. Measure the distance from the lens to the screen. That will give you approximate focal length. Then what do? Rearrange the position, measure the approximate focal length, make a mark. Keep the object slightly beyond the focal. Now, why beyond the focal? So you get a real image. Real image is formed here. If you keep your eye, you can see the image here on top. Now, the objective is you must find the image location. How are you going to find the image location? You keep another pin P2 like this. Now you can see the pin, you can see the image from this part of the lens. Now since they are coinciding like this, they will seem like to touch. Now you all don't get what you call, think it's touching or in the same place. Now you must move up your head in the lateral direction. If you move your head in the lateral direction with the body, move in the lateral direction, the image, in this case, they are not coinciding. The image and the pin will move relative to each other. There's a relative motion. If there is a relative motion, we say they don't coincide with each other. When the eye is moved in the lateral direction, there will be a relative motion. I and P2 are not coinciding. Not coinciding. Right. Then what do? While your eye is here, change the position of P2. Keep changing, keep moving your head in the lateral direction. One point, there will be no relative motion. What do you mean by no relative motion? Image and pin both will move together. That means that they are coinciding. Then what do? Measure the distance from the lens to the pin P2. That is your image distance. That is your image distance. That is your image distance. Now like this. Change the position of U. Measure V. Change the position of U. Measure V. Continuously do this. Plot a table. Measure 1 over U, 1 over V. 1 over U is your X. 1 over V is your Y. Plot 1 over V versus 1 over U graph. From the y-intercept, you can find the focal. Okay, now? Let's write. Let's write. So I name these figure 1. I'll name this figure 2. I'll name this figure 3. And there you go. That's right. Apparatus needed. Apparatus needed. Convex lens mounted on a stand. Convex lens mounted on a stand. Convex lens mounted on a stand. Next one, 2 optical pins. 2 optical pins. 2 optical pins. Meter ruler. Meter ruler. And white screen. Meter ruler and white screen. Meter ruler and white screen. That's right. Procedure. Procedure. Fix the apparatus as shown in figure 1. Fix the apparatus as shown in figure 1. Fix the apparatus as shown in figure 1. Adjust the position of the wooden support. Adjust the position of the wooden support. Such that light rays from a far object will pass through the lens. Light rays from a far object will pass through the lens. Light rays from a far object will pass through the lens. Light rays from a far object will pass through the lens. We adjust the position. We adjust the position of the wooden support. Of the wooden support along the chalk line drawn. Along the chalk line drawn from the right screen. Along the chalk line drawn from the right screen, such that a clear intense image is formed on the screen. Such that a clear intense image is formed on the screen. Such that a clear intense image is formed on the screen. Clear intense image is formed on the screen. Clear intense image is formed on the screen. And we measure the distance from the lens to the screen. And we measure the distance from the lens to the screen. And we measure the distance from the lens to the screen. And this would give us the approximate focal length. And this would give us the approximate focal length. And this would give us the approximate focal length. Okay. Right. Quickly draw this one. Figure 1. Draw figure 1. Draw. If you are finished, just indicate in the chat. Huh? If you are finished drawing, indicate in the chat. If you are finished drawing, indicate in the chat. Huh? Have you finished writing? Okay. Done. Right. Point number 2. Point number 2. Point number 2. We adjust the position of the lens on the chalk line. We adjust the position of the lens on the chalk line. We adjust the position of the lens on the chalk line. And we mark the approximate focal length with a chalk mark. And we mark the approximate focal length with a chalk mark. We mark the approximate focal length with a chalk mark. We mark the approximate focal length with a chalk mark. And we place the optical pin P1. And we place the optical pin P1. And we place the optical pin P1 just beyond the focal. And we place the optical pin P1 just beyond the focal. Just beyond the focal. Just beyond the focal. And we view from the opposite side as shown in figure 2. And we view from the opposite side as shown in figure 2. And we view from the opposite side as shown in figure 2. We view from the opposite side as shown in figure 2. Full stop. Next line right. We would see an inverted magnified image of the pin P1. We would see an inverted magnified image of pin P1. We would see an inverted magnified image of P1. And to find the location of the image, we We use another locating pin P2. We use another locating pin P2. We use another locating pin P2. Full stop. Next line. We change the position of pin P2. We change the position of pin P2. We change the position of pin P2. And we move the eye in the lateral direction. And we move the eye in the lateral direction. Now this is lateral, that's lateral, okay? And we move the eye in the lateral direction. If the image and P2 are not coinciding, if the image and P2 are not coinciding, here, not coinciding, there will be a relative motion. There will be a relative motion. There will be a relative motion between the image and pin P2. Between the image and pin P2. There will be a relative motion between the image and pin P2. There will be a relative motion between the image and pin P2. Full stop. Next point. At one instant, the image and pin P2 coincide with each other. The image and pin P2 coincide with each other. Image and pin P2 coincide with each other. Image and pin P2 coincide with each other. Then there will be no relative motion. Then there will be no relative motion. Then there will be no relative motion between I and P2. Between I and P2. There will be no relative motion between I and P2. I and P2. When the eye is moved in the lateral direction, I means EIE, yeah? When the eye is moved in the lateral direction. When the eye is moved in the lateral direction. Okay. As shown in figure 3. As shown in figure 3. Draw. Figure 2 draw. After you draw, indicate in the chat. Then I'll change to figure 3. Draw. If you have a doubt, ask. If you're finished, let me know. Right. Okay then. I go to figure 3. Draw. This is figure 3. Figure 3. If you're finished, let me know. Have you all finished? Done? Okay. Right. Okay, now. Next point, right. Next point, right. Using the meter ruler, we measure the object distance. We measure the object distance and the image distance. We measure the object distance and the image distance. And the image distance. Full stop. Next line. For different object distances, for different object distances, we measure different image distances. We measure different image distances. We measure different image distances as shown in the figure. As shown in the figure. We measure different image distances as shown in the figure. As shown in the figure. We plot a table between U and V. We plot a table between U and V. We plot a table between U and V. And we draw a graph between 1 over U and 1 over V. And we draw a graph between 1 over U and 1 over V. And we draw a graph between 1 over U and 1 over V. Using the y-intercept. Using the y-intercept. Using the y-intercept. We can find the focal length. We can find the focal length. Using the y-intercept, we can find the focal length. Okay. Draw, finish it off. So this is 21.1 now. You can see the practical, it's a pretty direct practical. How to find the focal length of a convex lens for a real image. For real. Once you finish writing, let me know. Finished? Okay. Right. Okay. Final part of the practical. Practical 21.2. Right. Finding the focal length of a concave lens. Finding the focal length of a concave lens. Finding the focal length of a concave lens using no parallax method. Using no parallax method. So when they say no parallax method, that lateral thing, that's the practical. Using no parallax method. Right. Now, what do you know about concave lenses? Whatever happens, you will always get virtual upright diminished images. So virtual upright diminished images means there is nothing for you to go and find the focal. Now, convex lens, we found approximate focal length. No. Here, no need. Because whatever you do, you're always going to get what? Virtual upright diminished image. Right. Now, you might ask me, then say, why are you using a widescreen? Remember, the widescreen is not just to get the intense image to find the focal. From the widescreen, we are stopping what? Visual obstructions from surrounding objects. That point will write at the end. Now, if this widescreen was not there, light from other objects also will go through these form images. So you can clearly see the image of the pin. So what the background widescreen does is, it stops visual obstructions from the surrounding objects. Okay, so the widescreen is important. You make a chalk mark, and we have a stand, On this stand, we have a concave lens. On this stand, we have a concave lens. Right. Now we have a problem. What is the problem? If you keep the object pin here, image is going to be diminished. So to make it easier, write this separately, widescreen. So here widescreen. What we do is, we hang the pin using a peg line. We hang the pin. When we hang the pin, what will we get? Virtual upright diminished image, no? I think I put it in this color. Virtual upright diminished image. There you go, the image. Now when I look from this side, you will be able to see this image. Remember, it's virtual upright diminished. Diminished image. That means very thin, like this. Smaller than the object. That's the image. So object distance I can find. No problem, no. Object distance we can find from top. Even here we can measure. How will you find the image distance? We use a small technique here. We place a plane mirror here. We place a plane mirror there. And we use a tall indicator pin or locating pin, P2. Now if you look through this, this part you have the lens, this part you can see the mirror, plane mirror, here mirror, here concave lens. Now from the mirror, what will I see? I can see part of the concave lens, I can see part of the mirror. From the lens, I can see this image. From the mirror, I can see this image. Now the image is going to be here. Image of P2. Image of P2. So image of P2. This is going to be image of P1. Finished. Now think carefully and answer. Through a mirror, object distance equals image distance. Image is here. Image of P2 is here. Are they coinciding? No. How do I know they are not coinciding? When I move the eye in the lateral direction, these two images will have a relative motion. Right? That's the rule. If they are not coinciding, when I move the eye in the lateral direction, there should be a relative motion. So this is the image of P2. That's the image of P1. Are they coinciding? No. So IP1 and IP2 are not coinciding. Therefore, when the eye is moved laterally, when eye is moved laterally, there is a relative motion. There is a relative motion. There is a relative motion. So when eye is moved laterally, there is a relative motion. Then what do? I change the position of P2. So when object distance here increases, image distance also will increase. Clear? Now what? Same story. So now here you have concave lens, mirror is here, pin P2 is kept here, object distance, image is formed here, image of P2. Object pin P1 is hung here. Image of P1 is formed here. Image of P1 is formed here. Now when I look through this, half lens, half mirror, image of P2 is here, Image of P1 is here. Image of P1 is here. When I move the eye in the lateral direction, they are coinciding, no relative motion. So when the eye is moved laterally, no relative motion. No relative motion between IP1 and IP2. No relative motion. No relative motion means they are coinciding. Now look at this. This is object distance. How do you measure the image distance? Simple. First, this is X. If that is X, object to mirror, image to mirror, this is also X. Let's say the distance between the mirror and the lens is Y. Then what can you say about the image distance? What can you say about the image distance here? Image distance here is going to be what? Here X, here Y. This is X minus Y. X minus Y is the image location. Understood? Now what? Change the position of the object. Image will form a new position. Change the position of P2 means changing X. You can keep this fixed. X minus Y is image distance. Like this, for different object distances, you measure different image distances. Any value more than 7 values is great. Greater the numbers, greater the spread. And you find 1 over U and 1 over V. Find 1 over U and 1 over V. Apply lens equation 1 over V minus 1 over U equal 1 over F. Object is also positive, image is also positive, right? Concave, no? Focal length of concave is anyway positive. 1 over V, 1 over U plus 1 over F. Graph is of the form Y is equal to X plus C. If you plot the graph, 1 over U per centimeter, 1 over V per centimeter. So remember, these are per centimeter values. Y equal X plus C. Y equal X plus C means you have a graph like this. Y equal X plus C. Don't forget to mark the origin. That's 0, 0. Even the earlier problem, don't forget to mark the origin. Huh? Turn back, quickly mark. 0, 0. Now what? Simple so. Y-intercept 1 over F. F is equal to 1 over Y-intercept. Finished. Again, I'll explain the practical from the beginning. Now, what are we using this? We are using this to find the concave lens focal length. These are wooden support. I'll name this figure 4. Place the concave lens on the wooden support. Hang the object pin. Virtual upright diminished image is formed. How do I coincide this? I use a much more taller pin with a mirror, plane mirror connected. Object distance equal image distance, image of P2 and image of P1 are not coinciding. So you have the mirror and you have the lens they seems like coinciding, but actually they are not coinciding. So when you move the eye in the lateral direction, in and out of the paper, there will be a relative motion. There is a relative motion. There will be a relative motion. I will erase that and write it here, no, because IP1, IP2 are not coinciding. So there is a relative motion. There is a relative motion. Right, short form we can write. Then what do you do? Change the position of P2 while moving the eye in the lateral direction. At one moment, image of P1 and image of P2 will coincide. Then there is no relative motion. No relative motion. Measure the distance here x. Object distance equal image distance. Distance between lens and mirror y. X minus y is image distance. Then what do you do? For different objects, object distances, measure different image distances, find 1 over u, 1 over v. Plot the graph between 1 over u and 1 over v. From the y-intercept, you can find the focal. Is it clear? Understood? Okay. This is figure 4. I'll name this figure 5. Clear, no? Clear? You can indicate in the chat. Someone is saying, is it a must to hang the pin? Now, in the practical booklet given, it is given as hanging the pin. So you must always follow that method. Huh? I will also show you without hanging the pin how to do. But in your practical booklet, it is shown or it is told to hang the pin and do. So according to the practical booklet, you do, because your exam questions will be based on your practical booklet. Without hanging the pin, how to do? As I will show after you write this. Okay, no? Right? But the most important thing is okay. Clear? Clear? Can you hear? Check one. Right. Now, earlier one person, yes. Always follow the practical guide. Practical guide is given as you have to hang the pin and work. I will show you also after we write this, without hanging the pin, how to work this. But it's mandatory how you should follow the practical booklet. Okay, no? Practical booklet is what they have given you. They have hung the pin always. Okay, let's write. Apparatus needed. Apparatus needed. Concave lens mounted on a stand. concave lens mounted on a stand. Two optical pins. Two optical pins. Two optical pins. A plane mirror. A plane mirror. A meter ruler and a white screen. A meter ruler and a white screen. A meter ruler and a white screen. That's right. Proceed, yeah. Step number 1. We connect the apparatus as shown in the figure. We connect the apparatus as shown in the figure. We connect the apparatus as shown in the figure. And using a peg line, we hang pin P1. We hang pin P1. We hang pin P1 such that a virtual upright diminished image of P1 is formed. Such that a virtual upright diminished image of P1 is formed. Such that a virtual upright diminished image of P1 is formed. Virtual upright diminished image of P1 is formed. Keep writing. To locate this image location, we use a plane mirror. We use a plane mirror with a taller optical pin as shown in the figure. We use a plane mirror with a taller optical or locating pin as shown in the figure. Taller optical pin as shown in the figure. We can see the image formed through the lens. We can see the image formed through the lens. And we can see the image formed through the mirror. And we can see the image formed through the mirror. And we can see the image formed through the mirror. Next point, right? As shown in figure 4, image of P1 and image of P2, image of P1 and image of P2, image of P1 and image of P2 do not coincide with each other. Do not coincide with each other. Image of P1 and image of P2 do not coincide with each other. So when we move the eye in the lateral direction, there is a relative motion between the images. There is a relative motion between the images. The keyword is a relative motion. Huh? There is a relative motion between the images. There is a relative motion between the images. Next point. Next point. While moving the eye in the lateral direction, while moving the eye in the lateral direction, we adjust the position of pin P2. We adjust the position of pin P2. We adjust the position of pin P2. And at one instant, the image of P1 will coincide with the image of P2. The image of P1 will coincide with the image of P2. The image of P1 will coincide with the image of P2. The image of P1 will coincide with the image of P2. And there is no relative motion. And there is no relative motion when the eye is moved in the lateral direction. There is no relative motion when the eye is moved in the lateral direction. There is no relative motion when the eye is moved in the lateral direction. Full stop. Next line. By measuring x and y, by measuring x and y, by measuring x and y, we can find the image distance. By measuring x and y, we can find the image distance. By measuring x and y, we can find the image distance. Okay, no? Draw figure 4, draw figure 5. Draw figure 4, draw figure 5. Once you finish drawing, indicate in the chat. If you have finished, indicate. Huh? Indicate. Indicate in the chat if you have finished. Done? Finished? Right. Figure 5. Work. Figure number 5. Draw. You have finished, indicate. Right? If you finish, indicate. Huh? Four or five people have said okay. Others also, if you have finished, quickly tell. Okay. Right. Next point, right? Next point, right? For different object distances, we can find different image distances. We can find different image distances. We can find different image distances. Inside brackets, right? X will change. You can keep this as a fixed distance. X will change. X will change. Therefore, x minus y will be different. X will change. Therefore, x minus y will change. We'll write like that. X will change because different object distances means different image distances. So different pin position for P2. So x will change. Therefore, x minus y will change. Close brackets. So for different object distances, measure different image distances. And plot the graph between 1 over u and 1 over v. And plot the graph between 1 over u and 1 over v. Plot the graph between 1 over u and 1 over v. Plot the graph between 1 over u and 1 over v. From the gradient of the y-intercept of the graph, sorry. From the y-intercept of the graph, we can find the focal length. From the y-intercept of the graph, we can find the focal length. From the y-intercept of the graph, we can find the focal length. Okay. Write this down and finish it. Write it and indicate that you are finished. If you are finished, indicate. Right. Okay. Put a small note and write this. Note. Note. The widescreen is used. The widescreen is used to avoid visual obstructions from surrounding objects. To avoid visual obstructions from surrounding objects. The widescreen is used to avoid visual obstructions from surrounding objects. Okay, second point. To plot the graph, we need a good spread of values. To plot the graph, we need a good spread of values. To plot the graph, we need a good spread of values. So we must choose U and V. So we must choose U and V so that there is a good spread. So that there is a good spread. So that there is a good spread. Next point. Next point. When we move the eye in the lateral direction, when we move the eye in the lateral direction, repeat it for the same object distance. Repeat it for the same object distance. A minimum at least 3 times. A minimum at least 3 times. When we find the object, when we find the image distance. When we find the image distance. When we find the image distance. So for every object distance, you repeat it at least 3 times. Double, triple check and see. Sometimes it might not vary much. If it varies, you find the average value. Okay. So a good average value for image distance can be found. So there are good average value for the image distance can be found. Good average value for the image distance can be found. Okay. Right. So that is it. Now, some of you are saying in school, sir, we did this in a different way. I know the method you already. Do the method. So here you have a, even this way you can do it. But I wrote what was given in the practical booklet. Huh? That's standard. No? Right. Very good. What we do is, we use a tall lens, a tall optical pin. We use a tall optical pin. We use a tall optical pin. Huh? When we use a tall optical pin, what happens is when light ray passes through, you will get a diminished image. Huh? You will sometimes get a diminished image. The taller it is, the better. Then your diminished image will be like this. diminished image will be like this. Image of P1. Right now? Image of P1. When we keep a plane mirror here, and we keep another similar pin here, P2. Look from this side. You will see half of the lens and half of the mirror. You will see part of this image here on top. And you will see this pin here at the bottom. So image of P2, this is the image of P1. So if this distance is x and the image is also here, image of P2 is also here, this distance is also x, this is y, x minus y is image distance. That means when I move the eye in the lateral direction, there is no relative motion. No relative motion. So this distance x, this is y, this is x minus y. X minus y image distance can be found. This is your object distance. Right now? This is the method, right? This is the method, right? Huh? Earlier somebody was asking this. This is the method, right? I'm sure this is the method you learned. Okay, no? So this method also can be done without hanging the pin. Use a tall pin P1. This will give you what? A diminished taller image. A diminished taller image. Okay, no? This is the method. Guarantee this is the only method. I mean, you have used a taller pin here. You get a taller image there. Use a plane mirror. This image and the image of P1, you can see the image of P1 above this, above the mirror. And you can see the image of this in the mirror. Move your eye in the lateral direction, no relative motion. From this source, you can find the object distance and the image distance. Okay, no? Guarantee this is the method. Okay, no? But hanging the optical pin is given in your practical book, so that's my duty to teach that. But most teachers, they teach this as well. You can draw this down. Put a small stand, right? Using a tall pin P1, using a taller pin P1, without hanging the object pin, we can do the same experiment. Without hanging the object pin P1, we can do the same experiment. We can do the same experiment as shown below. Draw this. So if they give this source, it's okay. Okay, no? Draw. Once you finish, let me know. Huh? Finished? Have you finished? Have you finished? Only 2 people have said done. When the others also finished, let me know. Okay then. All your waves practicals are done and finished, right? So now you can write all the past paper practicals which are given in your tute. That also we will discuss it in a, we will do like this, we'll do a discussion like this. So write and finish everything, huh? Because everything is done and finished. Okay. So all waves practicals completed. I hope you all understood it. Any doubts you can ask, there is no problem. So enough for today, right? Stay home safe. Take care.